Hello and welcome to the Machine Learning Podcast, the podcast about going from idea to delivery with machine learning.
Your host is Tobias Macey, and today I'm interviewing Jeremy Stanley about his work at Anomalo, applying ML to the problem of data quality monitoring. So, Jeremy, can you start by introducing yourself?
Absolutely, Tobias. Hi, everyone. My name is Jeremy Stanley. I'm the CTO and co-founder here at Anomalo.
And do you remember how you first got started working in machine learning?
Yes, vividly. It wasn't called machine learning when I got started in it. I'm going to date myself already. I did an undergrad in math and convinced myself I was going to get a PhD in math and went through most of the coursework for that PhD, did research, all in partial differential equations. So I, was deep in the theoretical side. I did some applied work and worked with tools like MATLAB and Mathematica. And then realized I didn't want to be a mathematician and try to vie for a handful of really good math PhD research positions. And so I went into industry and I got a job at an insurance company. And this was around 2000, right after the dot-com bust. And so you could convince an insurance company to hire somebody with a math background. And I started taking the actuarial exams, believe it or not, which were terribly boring. And I went through the first couple of them and then somehow convinced the management of the insurance company I was at that we could use deep learning models. Well, they weren't that. They were just neural nets back then. Use neural networks to predict the mortality risk for people that were trying to get life insurance and were being denied for it due to pre-existing conditions. And so using a ton of open data on survival outcomes and complex information about the diagnosis and prognosis of the folks, could you get to a better estimate of that? And I had no idea what I was doing. I was reading Christopher Bishop's Neural Networks for Pattern Recognition book, and I just read the book cover to cover and did all of the exercises. And at the time, started coding it all in C++, without any real idea what I was doing, and created a prototype to do this. And it never would have worked. There wasn't enough data. Neural networks were not the right tool at the time. And so it was all kind of a fantasy at the time, but I was enthralled with it and what could potentially be done with it. And I ultimately used that experience to go to Ernst & Young, a big consulting firm, and learn how to build predictive models, was what we called it at the time, to predict insured behavior. And I went from kind of off the deep end, coding things in C++, not even understanding databases, to, okay, let's go all the way back to statistics and regression models and kind of basic technologies and tools, and try to do it in the right way. And spent about 4 or 5 years there doing that, and kind of really, really helpful experience to try to use small data sets with rare and extreme outcomes, and working with a bunch of really smart statisticians and mathematicians to try to build models to predict insured behavior.
And so in terms of what you're doing now at Anomalo, can you describe a bit about what it is and some of the story behind it and why you decided that you wanted to spend your time and energy on this specific problem of data quality monitoring?
Yeah, from those early days of using machine learning models to predict insurance behavior, I've gone through a bunch of different technology companies, ranging from advertising technology for real-time bidding systems to building models to do recommendations for commerce and publishing platforms, to being at Instacart, which is where I was before Anomalo. I ran data science and machine learning at Instacart and worked on a lot of really interesting problems, ranging from logistics, routing, supply and demand forecasting, things on the marketplace side with recommendations and personalization, on the catalog side with enrichment of the catalog data. So a lot of really interesting challenges, and encountered tons of data quality issues along the way in all of those different scenarios and venues. And I left Instacart, it's been about 4.5 years ago, and my co-founder left a little bit after I did, Elliot. He ran product and growth. And we got together and knew we wanted to work with one another. We'd worked really closely together at Instacart. We're both on the exec team and working on some really interesting problems together. And trusted one another and thought in similar ways about some of the data problems that Instacart was facing. And so we got together and put together all of our best ideas for, well, what kind of a startup should we do? What are the best ideas that we each had? Put them on a whiteboard, talked each other through them, and data quality was one that rose to the top. There was one other, which I don't have to go into right now, that we played with and built for a little while. But data quality, it really resonated with us for two reasons. One is we both, Elliot as a product exec, seeing it and trying to drive and make intelligent growth decisions all around data. And myself, building machine learning models, recommendation systems, analytics practices, data engineering workflows, seeing data quality constantly, kind of cripple and prevent businesses from being effective with data. So we knew there was a real problem there. And we'd looked at, the market of the kinds of tools that were out there. And the state of the art was build a bunch of rules. And we had done this at Instacart. We had a system that had, 1,000 different rules that had been coded in SQL by, data scientists, ML engineers, product engineers, analysts. And it just didn't scale. We were constantly hitting data quality issues that we hadn't written a rule for, and constantly having to maintain and update all of those rules. And so that was the state of the technology landscape around it. And we knew we could do something fundamentally better.
And what is the role of machine learning in the product that you built, and why did you decide that machine learning was the proper hammer for this particular nail?
So there's really, as I've spent a lot of time on this, have come to the conclusion there's three different ways of thinking about data quality, three different kind of approaches or concepts that you can apply. The first one are rules, validation. We call them validation rules, right? A hard and fast constraint about the data. And what's beautiful about validation rules is it's actually the only way for an expert, a subject matter expert about the data, to express their expectation about what the data should look like. Using their knowledge about the system that generated the data or about the business that the data is in context with, right? They can express that knowledge and validate whether or not it is true in the data. Now, the downside with validation rules is they're incredibly difficult to scale. If you've got thousands of tables with hundreds of columns, and each table might have hundreds of meaningful segments of data, who is going to write all of the rules for all of those segments, for all of those columns, for all of those tables, and then who's going to maintain them over time as the data changes and evolves? And so it's just not scalable. And I like to compare it to testing software. When you test software, you can write unit tests, and the unit test that passes today will pass tomorrow, will pass the next day until the code changes. Data is much, much more chaotic, right? Data is constantly changing and evolving for a wide variety of reasons. And so you need, if you're going to measure the quality of data in a production system in the real world, you need something that can adapt to that chaos and can scale to the scope of data that companies are capturing and dependent upon. So the other two approaches that use machine learning, one is time series, metric-based monitoring. So instead of creating a rule, instead define all of the metrics that you care about and monitor all of those metrics for unusual changes. And it's a pretty powerful tool as well. The main problem with that is if you try to boil the ocean and compute all of the metrics, right, for all of the tables, all of the columns, all of the segments, you end up with this huge deluge of alerts coming from a bunch of metrics that are always changing. There's always going to be something changing in any given table at any given time. And the question is, does it really matter? And how do you kind of cluster and group all of those things together so that you have a meaningful story about a change in the data? And so the final approach, one that we've invested the most in, is what we call unsupervised data monitoring. And it's essentially building a machine learning model to detect material changes in a table, and to do that and be able to allocate the changes down to individual records. And the point of this is to have one algorithm you can point at a table, and it can online learn about that table and changes that are happening in the data over time, to be able to detect really unusual changes that could be adverse and then explain those changes to the end user without having to boil the ocean and compute a whole bunch of different metrics. And so I can tell you more about that algorithm and what it does and why it's useful. But if we kind of compare and contrast these three different approaches, just to fully set the stage, the downside to this unsupervised algorithm is it is sampling the data. It can't analyze every record. and it's statistical in nature. So it's never going to find a needle in the haystack, right? And so compare that to the validation rules. The validation rules, you can use those to say the data is perfect in some way, and you can have the user bring their subject matter expertise. If you contrast it to the metrics, when you define a metric, you say, I really care about the time it takes for a user to complete this event. You're saying that the slice of data in a table that's used to compute that metric matters to you a great deal. And you want to be really sensitive to changes in it. And so that's a useful thing to solicit from a user. The unsupervised monitoring, it's going to treat every row, every column as being equally important and pay as close attention to them all.
And in terms of the particular machine learning approaches that you are using, I'm wondering if you can talk through some of the kind of categories of machine learning and the different paradigms that you're applying to be able to address some of the specific capabilities of data quality monitoring and specific types of alerts or information that you're trying to surface with those particular ML approaches.
So the time series, approaches are pretty straightforward, right? It's time series anomaly detection. The specific context of it is a little bit different from what is often time series are used for. Often time series are used to make longer term projections, right, over the course of multiple days or multiple time periods. Here we're interested in how unusual is the most recent value in any given time series, and being able to quantify the degree of unusualness, right? So we need to have really good confidence intervals, or actually ultimately be able to estimate the quantile, right? How unlikely is any given observation that arrives for the most recent observation in a time series? And then we want to be able to help explain that and kind of characterize how and why the time series model fit what it did. And so you need to be able to tell a story around it. The more complex machine learning is in the unsupervised, where we're just pointing the algorithm at a table and asking it to detect material changes in the table. And the way that works, I can walk you through it. So imagine, let's simplify the situation. Imagine we have a set of data from a random sample of records from today in a given table and a random sample of records from yesterday. And I want to find out, well, has something changed in the data from yesterday to today? So one of the insights that we use is if you build a machine learning model and turns that into a classification problem, try to predict on which day did each record arrive on. You can use an algorithm like gradient boosted decision trees to predict, okay, label yesterday's records as 0, today's records as 1, and try to predict 0 versus 1. If the gradient boosted decision tree can't learn anything about the labeling of the zeros and ones, then you can conclude that the data from yesterday and from today was drawn from the same data generating distribution, right? Same data generating process. If it finds that there's some material difference, then you can use algorithms like Shapley values to identify, well, exactly where in the data did that change originate from, what columns, what values, and then you can begin to characterize that change to identify, is it happening in a specific segment, in specific columns or groups of columns in the table. And so that's the core of the algorithm. And what we're trying to detect are unusual changes happening in the table. And I'll talk a little bit more about that because that's actually a part of what makes it hard, is how do you identify what changes are unusual? But the specific things we'd love to know about range from simple things like there's a big increase in null values in a column. And it could be the column was never null, or it could be the column was always 10 to 15% null. And all of a sudden it's shot up to 18 or 20 or 25% null in an unseasonable way, right? Maybe the null values are higher on Mondays, but today's a Tuesday, and so you wouldn't expect to have that many null values on a Tuesday. Or it could be a drop in a segment of records. So I'm a social media platform, and I'm measuring all of the events in my social media platform. There's 150 different types of events. And if one of those events suddenly starts firing 10% as often as it normally does, I'd love to know about that, right? That's an unexpected change in the distribution that I would care about. It could be a distribution change in one of the columns. It could be a credit scoring data set, and you've got credit scores in it, and those scores typically are normally distributed centered around 700, and all of a sudden they've skewed to the right, and that would be a really important change that you'd want to know about. Or it could even be the relationship between two columns has changed. Column X is always this value and column Y is this value. And now all of a sudden that relationship is broken. Maybe some join upstream is failing, or identifiers are changing in some way, and the relationships have changed. So all of those changes that I've described, you can detect in this setup that I described of label yesterday as 0 and today as 1. Because there's going to be a significant distributional change in the data labeled ones versus zeros. The thing that makes it actually really difficult, well, there's a couple, but one of them makes it really difficult is there's lots of other things that constantly change in data. And so how do you control for them? And some of them are mundane and obvious, like the date, right? There's always a created at. That created at is always getting bigger. And so, your gradient boosted decision tree is going to obviously identify that the created at, if it's encoded as a seconds as an epoch, right? That's always larger on one data set than the other. And so you need to be able to remove things like that. Another example would be integer IDs that are auto incrementing, again, always getting larger. But then there'll be a lot of things that are more subtle. And it really comes down to how chaotic the underlying data is. And so the way I like to think about this is there are some data sets where, barring some structural change, maybe in the system that's generating the data, and barring maybe some day of week seasonality that you can control for, the distribution shouldn't be changing that often. And it's going to be pretty consistent one day to the next. There are other data sets where they are changing all the time. And so the most common example is any data set where there are humans in some control structure in that data set taking actions and affecting the data in a material way. A good example is marketing data sets. Marketing data sets are influenced by campaigns. Campaigns are influenced by marketing managers. They are setting up campaigns to start and end at random periods and doing experiments. And that data is just going to be full of chaos, right? Not only are the campaign IDs changing, but the targeting parameters of the campaigns are changing. And so the geographic distribution and the channels that the data is hitting are changing. And so the other big part of what we do is we take this underlying algorithm that is able to detect changes from one day to the next, and we capture lots of metadata about it. And it comes down to the SHAP values and summaries of all those SHAP values. And we use that metadata to detect how chaotic different features of the data are over time, and to dampen those, and to essentially set higher thresholds for the algorithm to detect material changes, or in some cases kick the features out altogether because they're simply too chaotic.
And in terms of the characteristics of the data that you're working with and kind of the scale and potential issues with quality or variability, I'm curious how that influences or constrains the types of algorithmic approaches that you're using to build and train your models, and some of the issues around kind of latency and accuracy that you also have to contend with to be able to kind of hit the optimal point for being able to deliver the features that you're promising to your users.
Yeah, there's a bunch of interesting things there. The first one is, and so I can describe some of the requirements and context that we're operating in. So one important piece is that this is being deployed often in a VPC environment with big public companies, could be financial services companies. We work with a company that does identity management for the federal government, for IRS tax returns. These are companies that cannot take any risk whatsoever with the data that they have in their data warehouse being exposed to the public internet or being exposed to SaaS providers. And so the algorithms need to run in this fully autonomous environment without us even having a lot of insight into them in many cases. They need to run across data from wildly different verticals. So it could be a connected healthcare device. It could be a real estate company aggregating MLS listings data. It could be an e-commerce application. It could be financial services and insurance. It could be anything under the sun. And then it needs to work across all of the different common cloud data warehouses and all of the SQL variants that they support. And so the scalability side of it, the data sets can have one record a day, right? So they can be very, very small, very important. data. And so one of the companies that we work with is Carta. They don't have a tremendous number of transactions. There's not huge volumes of equity transactions, but each transaction is very important. Or it could be a social media platform that we work with where they're tracking every event in the platform, and it's 40 billion records a day. And so a huge number of records. So it can be a very large scalability in terms of number of rows. Can also be pretty wide in terms of number of columns. Most tables have somewhere between 5 and 50 columns, but we have some customers with tables that for some reason have 1,000 columns in them. And so oftentimes our algorithms need to scale with number of rows times number of columns, which can be challenging in those situations. So that's some of the context. In terms of latency and runtimes, the algorithms themselves are usually running on a daily cadence. And so it's not something that needs to run in real time. Instead, it's each day analyze the most recent days worth of data to detect, are there any material data quality issues that are new and adverse in this data set that we should notify about. You can run it as often as every hour in some circumstances if you wanted to. In general, there's a trade-off there. And this comes to the accuracy piece. The more often you run it, the more likely you are to find something that you don't actually care about. And some human is going to have to look at that and interpret it. And we work really hard to explain things and produce a lot of visualizations and context and summaries to kind of lower the bar of how much work the human has to do to understand the issue. But still, if you're running it every hour, it's 24 times that you're flipping the coin of, am I going to find something? On smaller slices of data than if you're running it once daily.
I'm also curious about some of the kind of operational aspects of how you think about the optimizations that you want to spend your time and energy on for the models that you're building and training, and some of the ways that you're thinking about kind of the return on investment of what you're building versus how much it's costing you just to operate it, and how that impacts the ways that you're able to market and sell the product that you're building, the kind of margin management, and some of those operational challenges that you have to deal with to be able to use sophisticated algorithms for a task that is sometimes difficult to be able to compute the kind of return on investment for the end user.
Yeah, it's a tough question, and a big part of what I think differentiates Anomalo is our ability to do that well, if you really come down to it. In the very beginning, especially bootstrapping, it wasn't obvious to us, how do we tell if we're doing a good job or not, right? You don't have any customers in the very beginning. And then eventually you have pilots, but still it's small sample. And each customer is different. And so we've invested a lot in what we call a benchmarking process. And that benchmarking is using public data and data contributed by customers and design partners of ours. We take those data sets and we run our algorithms to detect anomalies on them as they are. And so we'll step through, say, 100 days of data in a table and measure everything about the performance of the algorithm, its runtime, its memory usage, and whether or not it flagged anomalies, how strong they were, where they were. And then we reset everything and run back through the data set another time, introducing chaos into the data. And we have a whole chaos library that we built early on. And this chaos library has about 50 different types of chaos that it can create. To give you an example, it could introduce null values. Or it could shuffle randomly the values in a column without changing their distribution. Or it could multiply them all by a constant. It could reverse the string order. It could delete data. It could add synthetic data. And so we have these different chaos functions, and we have a random chaos application that will draw a random chaos operator, draw a random table or column, draw a random fraction of data to apply that to, and then try to apply it. See if it's successful, because not all chaos operations can work with all data, and then keep trying until it gets one that's successful. And then that becomes an anomaly that's introduced, or a data quality issue that's introduced. And we ask the question in the benchmark application, is the algorithm able to recreate it? Is it able to identify that? And so now we can measure the ROC of the anomaly scores that the algorithm is spitting out, where we've got days where we haven't introduced any chaos are 0 outcomes, and days where we have are 1 outcomes. And then we can also answer, how accurate are we at identifying where the chaos was introduced and kind of correctly explaining. And so we will do this for, many, many different data sets, drawing many different random chaos samples. And we have an application that spins this up on spot instances and, runs this benchmark and produces a bunch of visualizations and analyses of the results. And, that's how we were able to iterate through to something that worked well. And each time we encountered something in the wild of, it looks like, there's a bunch of time columns in this data. And most of the time columns are all actually relative to the created at. And we're treating them as not being relative to the created at. And that's causing issues where we're saying that there are anomalies and there aren't, or we're not clustering them correctly. Let's try to fix that. We can introduce a change. In this case, the change might be just, compute the relative offset of all of the timestamps to the created at and use that as a feature instead. And are you now able to identify anomalies more accurately and explain them more accurately?
The explainability aspect is interesting as well. And I'm wondering how you think about kind of the types of explanations that you need to be able to produce and the level of detail that's necessary for the kind of predictions or discoveries that you find with your algorithmic approaches, and being able to present them in a meaningful context to the end user so that they can actually take some substantial action to either address or ignore the kind of discovery that you've made.
Yeah, we've learned a bunch of things about that. So, one of them is there's a wide variety of ways that you can summarize these issues. And the most powerful tool that we developed early on with these algorithms is the ability to, using Shapley values, take the results of the model and credit the anomaly down to each individual value in the table. And so you end up thinking about, I've got this sample of data from today and multiple different prior days. And in addition to the data as it exists, I have this kind of shadow matrix that's of the exact same shape. But all of the values in that matrix are floating point values indicating how anomalous that value appears to be. Using that, you can then summarize the issue by aggregating across rows or aggregating across columns. And what we do is we have algorithms that run on top of that and try to come up with a natural language explanation for the issue. The column X has a significant percentage increase in values Y that were not there before, or the distribution in column X has shifted. And we have what we call explainers of different classes that apply to that to try to turn it into natural language. And it's tricky to do that well. It's easy to end up having something that sounds reasonable in theory but comes out as being confusing. And so we actually have a pretty high threshold for only producing those if we're pretty confident they're reasonable. And below that, we kind of punt and say something complex has happened. And then everything else is visualizations. I mean, right, in the end, a picture is worth 1,000 words, right? A picture is worth 1,000,000 data points. And so in many cases, rather than trying to force ourselves into a natural language explanation, we'll create visualizations that could take the affected columns and summarize them in such a way that the specific values that were affected are highlighted, and you can easily compare the distribution one day to the next. And so that's a common way that we visualize things. The most effective way that we found to use this is to actually use it as a search algorithm for unexpected changes that are happening in the data. And then we take those and think about them as like hypotheses. It looks like it's possible that there's been a distribution shift in this column. Let's take that and now build a time series model that's going to pull the last year's worth of data. And let's make sure that the time series model is itself also anomalous. And then we can use the results of the time series model and show that to the customer and to the end user. And it will give them even more confidence because now they can see a much longer time series. And it can be presented in a way that is easier for them to wrap their head around than having to think about everything that the unsupervised algorithm itself did.
As you're talking about the operations and meta operations that are going on, it sounds like you have the machine learning models that are focused on the customer data and being able to run the detections there. And then you also have additional ML models that need to run against the outputs of the kind of first layer. And I'm curious how you are managing some of the operational and infrastructure aspects of being able to build and deploy and kind of automate the execution and retraining of these models so that you don't pull your hair out kind of having to keep a watch on every single thing.
Yeah, this is where some of I give myself some credit here for my experience building systems in many different contexts and kind of having made lots and lots of mistakes. And the things that I think we did here that really help us are, one, the models are retrained every time. We don't maintain any state. The models are constantly retrained, which sounds kind of crazy. Like, why would you do that? But it actually turns out to be a big advantage. And a part of the advantage of it is, obviously you don't have to maintain, statefulness of the models themselves. But also keep in mind, what are the models trying to do? The model training algorithm itself is what is telling us if there are anomalies. And so it's not like we're trying to train a model and then use that model to make predictions in lots of different contexts. Instead, it is the model training process itself that is of value to us. So we literally just retrain it and throw it away every day. And all that we save are summary statistics about the models. And then in order to leverage those summary statistics, we'll reload history of the summary statistics and use our time series models to process those. And so as long as we've benchmarked the algorithms for training the unsupervised learning well, and we've benchmarked the time series algorithms well, and we've got separate benchmarks for both of those, we can rely on them being accurate and reliable when they're built on demand each time the check runs. What are the constraints? What do you give up when you do this? Well, one, you can't use a deep learning algorithm for this. It would be infeasible to every day for every table for every customer. We're talking hundreds of millions of tables, right, to train a very complex model. The model needs to be able to train quickly, in say 5 minutes max. And so we actually sample the data aggressively to be able to ensure that we can do that. The downside to that is it does give there is a limit to how much the model can detect, right? It can't detect a 0.1% shift in a table if you're sampling 10,000 records. That's not going to be a large enough sample size to detect that small of a change. In practice, what we found is if you wanted to be sensitive to that small of a change, you would end up sending so many alerts that the users would walk away from the system. And so it's not even practical to find those things from the user's experience, even if you wanted to invest the computational resources.
As far as the tooling and platform design that you are building for being able to support this product, I'm curious, what are some of the key decision points that you look to for figuring out whether there is something that you can pull off the shelf versus what you have to build custom because of the specific constraints that you're working within?
Yeah, in the end, so everything is being deployed in our customer's environment in VPC. And it could be on a single instance inside of a bunch of Docker containers, or it can be in Kubernetes. And so what we can't do is use an AWS service, right, and make external calls to it, or any cloud service. So you can't do any of those things. It has to be inside of the containers, and you've got to ship everything that you need to the environment where this is going to be executed. And so ultimately, if our backend is Python, and so if there is a Python library that is licensed in a way that we can package and deploy it inside of the application, we can use it. If there isn't, we can't. And that makes it pretty straightforward. We do assume that there's a cloud storage bucket that the customer sets up that we have write and read access to have a long-term state. And then our application ships with a Postgres DB that we use to be able to store data about the algorithms that are running.
As you have been building out this platform and iterating on some of the algorithmic and operational aspects of building some of this kind of anomaly detection, what are some of the ways that your kind of scope and focus have shifted and evolved, and some of the ideas that you had going into this about how you might approach the problem have had to be kind of reconsidered or reworked?
I'll give you, there's a few things we could talk through here. Probably the first thing that I had to dispel, the first misconception I had to dispel, was I assumed that if there were unexpected changes happening in a table that someone was monitoring, that someone would want to know about that unexpected change. And in many cases, this is true, but in many cases, it's not. And the reason is a lot of companies maintain and collect a lot of data they don't know anything about, and they actually don't really care about. And so if you go into the average cloud data warehouse deployment, I would hazard to guess that you could go in and apply random chaos operations to 80% of the data, 80% of the columns that are being stored in that data warehouse, and no one would ever notice. And it wouldn't actually cause any harm because that data is not being used. It's not being used to drive a decision. It's not being used to drive a machine learning model. And so you have to be very careful about how you alert on things if people are tracking data they don't care about. I remember going to customers and walking them through a history of issues happening in tables in the very early days, and them kind of going around the room and going, well, I don't remember why that column is there. Does anybody know? And it's like, oh, well, Sarah recorded this 5 years ago and then left 4 years ago. And we don't know why, and no one uses it anymore, but it's just there. And suddenly it's null, but I don't think anybody cares. That's a pretty common story. And so we had to figure out ways of allowing users to target Anomalo at the data they cared about, and also constrain what we found and what we alerted on to only be really adverse issues that customers would obviously want to consume alerts about. So that was definitely one issue. I think another is the challenge of what we're dealing with, how long the tails are. A simple example is we need to be able to know how to tell time in a table. And that sounds kind of obvious. There should be a time column that everyone uses in any given table, if it's measuring time, that queries are going to be executed against. I've been surprised at the variety and types of how different time columns are measured, ranging from, yes, there is a created at timestamp to, oh, well, actually, it's stored in a string format, in a very specific string format. Or, oh, actually, it's stored in 3 different columns, year, month, and day, and they're each string formatted, and they don't have leading zeros in them. It's stored as an epic, right? And so our algorithms need to be able to translate the SQL queries that are executed to efficiently use those time columns to be able to get slices of the data in ways that don't require the warehouse to query the entirety of the data. Another interesting challenge we run into is you would think that sampling would prevent you from running out of memory, because we only ever take 10,000 records at a time, as an example. Well, what happens the first time you run on a table that is a bunch of API responses that include payloads from the API in the log data as JSON? And now a single row could be a gigabyte of data because it's got this massive JSON payload. And so how do you avoid ever actually pulling that into the application and running out of memory? And being proactive about that, and not just in strings, but also in arrays and other complex data types that are stored. And so it's amazing. Every week or two, we're kind of exponentially growing the number of customers and their use. And so you would expect there to continue to be new issues. And it's just surprising the frequency with which we keep encountering, oh, I never thought I would see a situation where data was stored in this way, in this kind of circumstance, and this general machine learning model needs to be able to handle it gracefully.
As far as the building of Anomalo, I'm curious, what are some of the ways that you're dogfooding the product to be able to actually iterate on the capabilities, as well as to be able to just run your own operations and make sure that you're working with data that is valid and meets your expectations as well?
So we've got a couple of fun things that we do there. One is we monitor a bunch of public data. And this is how we got started with Anomalo in the very beginning. We began with Google BigQuery has a public datasets project that you can connect to. And there's a lot of interesting public data from municipalities around the world, from all the cryptocurrency datasets. With the COVID pandemic, there were a bunch of projects to track data associated with COVID. One of my favorite datasets is this GDELT online news dataset that Google has put together, where they track news articles going over the wire from all over the world and they do NLP to identify which news articles are associated with COVID. They do sentiment analysis on it. And so it's a really fascinating data set that's, includes lots of geographic information and information about the URLs. And you can track the state of the news stream on the pandemic using Anomalo. So that was a great way to start. And we still do that today and kind of pressure test things in that environment frequently. And then as we've grown and added more customers, one thing that's challenging for us is like I said earlier, we deploy in VPC. And in many cases, customers don't want any data to come out of that environment. So not just data from their data warehouse, but even metadata about the tables that are being monitored or the columns in those tables. They might contain strategically valuable information about the initiatives the company is working on, the investments that they're making. And so even that data can't leave the environment. But in most of our environments, we're able to get exception tracebacks. We use Sentry. And so we can get all of the Sentry logs. And in some environments, like we run our own SaaS version of Anomalo, and some customers use that SaaS version, we can get a lot of monitoring. And so we are using dbt, moving that data and transforming that data in Snowflake, and we run Anomalo on top of that data. And we can detect sudden changes in usage in Anomalo. We can detect outages or structural problems happening in Anomalo that we wouldn't have detected otherwise if we weren't using Anomalo on Anomalo. The other fun thing that you can do in some cases is there are views inside of some data warehouses that are query level statistics. How many slots did a query consume? How long did it take to run? Who executed it? And so inside of our customers' deployments, we can use Anomalo to monitor Anomalo's queries and identify if there's anything unusual happening in the query distributions that are being executed by Anomalo.
In terms of the ways that Anomalo is being used or the ways that you've been able to apply machine learning in this context of data quality monitoring, what are some of the most interesting or innovative or unexpected experiences that you've had?
Yeah, I think the first one is just how a generic algorithm like what I've described is broadly relevant across every domain with structured data. There is a somewhat limited kind of surface area of the shape and structure of structured data, and it's why gradient boosted decision trees have been so effective. They can work with arbitrary data. You do have to come up with a automated encoding scheme, which is one of the pieces of IP that we had to build here. How do you intelligently encode into features every data set that you encounter? But then it really does work on everything. And every time we'll sit with a new customer and look at the kinds of results that are coming out of it, the signal to noise ratio is really, really high. And so that's been surprising. In terms of actual use cases that have been interesting, one fun aspect of Anomalo is in the end, it becomes this automated system that can execute queries against your data warehouse and analyze and visualize the results of those queries and tell you if something unusual has changed. And so we've been surprised at how this will start with a kind of core data quality initiative, but then people will latch onto the tool and start to use it for other purposes. And one is fraud and detecting unusual behavior. And so we've got several customers that have used Anomalo to detect individual entities that are doing unusual behaviors, spiking account creation or unusual usage patterns of a platform. And it's by no means a general purpose fraud tool. I would never encourage anyone, if you've got a fraud problem, there's a ton of work that you need to do in correctly collecting data around that problem and building a model and validating that model. But if you just want to detect unusual patterns for entities, that's something that we found a lot of customers use Anomalo for. Another interesting example, and this is one we facilitated, is the core algorithm that detects drift in data over time, right, that I described before. You can also take that algorithm, and we've decoupled it from time and have created a version of it where you just get to compare two SQL queries. And so you can use Anomalo and run this on a one-off basis or have it recurring, where you drop in SQL query A and SQL query B. And we will sample records from both of those queries. And they can be even across two different platforms. You could do, one could be from your Postgres secondary, and the other one could be from Snowflake. We'll take the samples from those two, run the machine learning algorithm to detect any differences and summarize them. And that opens up a whole bunch of interesting use cases. The obvious one is I want to compare two data sets, right? My production and my staging data set, maybe after some transformation, I want to see, did I affect the data and what was the distributional effect of the transformation? But you could also use it to say to compare the control group and the test group in an A/B test, and use this to identify, are there any meaningful differences in those two populations in this table? Or you could compare one marketing campaign to another marketing campaign and all the attribution data that you have and find out what are the meaningful distributional differences in those data. And so it ends up for customers that are savvy and kind of really, really using the product, they end up using it for a pretty wide variety of use cases.
And as far as your own experience of operating in this space and building these ML projects, what are some of the most interesting or unexpected or challenging lessons that you've learned, either about the problem of data quality monitoring or about some of the vagaries of machine learning itself?
I would say early in my career, when I was in insurance, explainability was paramount. You had to have explainability. You had to go through regulatory approval, or you had to be interacting with an underwriter who was going to make an important decision about a business or someone's care using the results of your model. And so explainability was paramount. And the way we achieved that was by keeping the models very simple. And that was kind of the general constraint. We would almost always just use generalized linear models and carefully constructed feature sets to try to make the models be explainable by default. Then I spent the next 10 years of my career in domains where explainability didn't matter at all. I'm just trying to make the most optimal bid on an advertising impression in 50 milliseconds. And I don't need to know why. Nobody needs to know why. If it works, it works. Or I just need to figure out how best to route 10,000 deliveries over the next X hours in Y markets. And in the end, we'll measure the delivery per labor hour. And if that's great, we've done our job. It doesn't really, you don't have to explain it. Explainability was important, but it was important for the modeler, to understand the physics of the world they were building models in, to come up with better hypotheses for how to improve the models. And so I was always a huge believer in visualization. And I fell in love with ggplot over a decade ago. Now we use Altair. And anytime I was involved in any machine learning initiative, if I was personally doing work on it, I would generate hundreds of different types of visualizations to try to look at the problem from many different angles. But it was all to build intuition versus to have something be explainable as a part of the product. And so I think in what we're doing now, the interesting challenge is, how do you build something that is generalizable and can work in arbitrary environments where we actually can't inspect what's happening ourselves, but is going to be explainable to the end user? And I think that's been SHAP values have been a big part of that, and then leveraging all of the visualization to create the narrative for the end user on top of that.
And for people who are working in this space of dealing with data quality issues, what are the cases where Anomalo is the wrong choice? Or maybe specifically to your product, what are some of the cases where machine learning is the wrong solution?
Yeah, I'll answer both of those questions. So, where machine learning is the wrong solution, I hinted to this earlier. If you know that a table should be unique on an ID, then the only way to ensure that is to test it, with a validation rule. Machine learning can tell you if the table was unique and suddenly became non-unique, but it can't tell you that it should have been unique from the very beginning and never was. And so the role of rules is still really important to bring to bear, the human subject matter experts' judgment about the data. And metrics, I think, are still really important, because when you declare a metric, you're saying this slice of data really matters to me. So one thing, going back to your earlier question about something we learned in the beginning, we were just building the unsupervised learning, and it was really powerful, but it wasn't a complete product, because you needed to be able to declare metrics and monitor them for unusual changes, because they matter and you want to pay attention to them, and you needed to be able to ensure the data was perfect in some ways. And so what we ultimately built was a system that could do all of these things together. And I think that's much, much more powerful, and it's scalable because of the unsupervised learning. You don't have to do rules. You do them when you want to. And I think that's a big distinction. Now, places where Anomalo is not the right choice, I think there are a lot of situations where you want to assess the data quality, the quality of data in a different context. And the context Anomalo is really good at is data is being updated regularly. Ideally each day, new data is arriving, if not much more faster than that. But there are some domains where the data arrives every quarter. And it's actually very difficult to use machine learning on quarterly data. I would almost argue it is impossible. The reason is you just don't have enough history. In order to get history, you'd have to go back, 10 years, 20 years to have enough history to make some judgment about whether or not changes in this quarter are unusual in an automated way. Well, almost all things about humans change dramatically over that time period. So unless your quarterly data is about, ice core measurements, right, from, geologic ages, like it's just not going to be stable enough. And so in those contexts, you've just got to rely on human judgments and rules. Another good example, we've talked to companies in pharma that do massive clinical trials. Those clinical trials will be one-off huge investments that will generate a giant corpus of data. And they'll want to understand the quality of that data. And because it kind of inherently lacks this notion of time and change, right? We're looking for regressions in data introduced by humans or changes in process. Because it lacks that, instead it's just this sudden big sample. That's not a very good use case for us either.
And as you continue to build and iterate on Anomalo and explore some of the different applications of machine learning to this problem space, what are some of the things you have planned for the near to medium term?
Yeah, so there's a bunch of exciting things that we're doing with Anomalo. One of the things is where we began Anomalo really focused on data quality, this kind of deeper dive into the data itself and understanding as the data changed, inside of the table, the actual records, their distribution, their values. But there's a lot of data that you can get about tables in modern warehouses just from metadata and from SQL queries. And so we're expanding Anomalo to use a lot more of that data to do more, fully automated monitoring for observability. And that's going to add a bunch of other features and functionality into Anomalo. And I think it will complement what we're doing in the deeper, fully automated data quality monitoring. So I think that's one really exciting thing that we're doing today. There's a lot of other things on the machine learning side itself where we can take the algorithms we've developed and continue to improve them and come up with, like I said earlier, using the algorithm as a search basis for interesting issues, and then fully qualifying those and explaining them with an additional layer on top. And so we want to continue to expand that, so that there's more ways that you can use Anomalo for anomaly detection and get really rich, fully validated explanations as well.
Are there any other aspects of the work that you're doing at Anomalo or the operational aspects of building and running these ML models or some of the kind of algorithmic or systems design questions that we didn't discuss yet that you'd like to cover before we close out the show?
I think that one of the most interesting things that we haven't really talked about, we talked about our benchmarking, but the other thing we haven't talked about is how we test these. We talked about the long tail that we're exposed to. And so, if I sit back and I think about, what is it makes this so difficult? In the end, we have around 100 different types of checks that have different types of business logic, use, variations of the machine learning algorithms, and SQL and just core business logic in them. Those 100 different checks, they need to apply to 10 different classes of data warehouses, ranging from Snowflake to Postgres to Azure Synapse to Oracle or Teradata, right? Each of which will have their own idiosyncrasies in how the SQL needs to be crafted and the nature of the types and the results that you'll get back. We need these to work for arbitrary data from arbitrary different verticals and different structures of data. We need them to work in an environment we don't control and have clear insight into. And finally, many of these algorithms are stable. They will be learning iteratively over time, storing metadata about their performance and improving over time. And so one of the biggest challenges is, well, how do you have good unit test coverage for that 5-dimensional space, right? And each time we encounter a new issue, we want to make sure that we never see that failure case again. We never throw that exception again or never miss that kind of an anomaly again. And so we have a really, really extensive unit test library, and we run those unit tests on a bunch of synthetic, data that we've created and replicated across every different backend that we support. And so we have, near 99% unit test coverage on the backend, code that runs all of this, and we'll run those unit tests on, every PR for each of the 10 different backends, and it's invaluable to have that. It means that we can, as the code base and the surface area continues to grow and get more complex, we can make complicated changes and refactor things and be very certain that we're not going to introduce issues and not be able to solve some of the long tail issues that we've encountered before. So I'm really glad we made that investment. It's been really, really valuable.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you and your team are doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest barrier to adoption for machine learning today.
It's interesting. I mean, it's a hard question to answer right now. And, a part of it is because of what we're seeing happen with large language models. In the past, I think if you'd asked me this 5 years ago, I would have said that the secret to a machine learning model being really effective in production is this combination of deep understanding of the problem you're trying to solve and how to develop the right fitness function for that problem that's going to meaningfully move, right, the objective. Combination of that with an understanding of the appropriate algorithm to bring to bear that can actually move that, and then the engineering, skill to be able to put that into production and manage it effectively. And getting all three of those things together is really hard. One of the things that I found most effective is to have, teams of people that have a shared common goal, where the success of the machine learning algorithm is that team's goal. And they've got, the product, the machine learning, the engineering skill sets all on one team working very, very closely together, reporting to the same person, right, trying to drive to that outcome. It's interesting now with these large language models that some of that is going away. Like these models can be applied to natural language in almost any form, and you can do it just through an API call. And so the generalization ability of the latest generations of models is really amazing. And I'm excited to see where that generalization ability continues to go from here. And at what point does it begin to apply to structured data? At what point will we be able to have models that can generalize across many different structured data sets? In the end, the business context and the fitness function and kind of how you integrate it into the product, that sense is always going to matter. And so probably that's still the place where I think the opportunity is missed most often. There's a ton of machine learning models that are put into production that never had a hope of having any impact because they weren't optimizing for the right objective. And oftentimes you won't find out about that for months or years to come. And so probably that's still the thing. But it's interesting how much is changing, and then also how many new tools are being developed to make the engineering side of developing models and putting them into production much, much easier. I don't really worry about those things today because we can't use a lot of them. Everything has to be deployed in VPC. And I'm not really in a position where I want to go back and question the decisions I made 4 years ago. But if I were starting something again today, I'm guessing the tool stack would look very different.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing at Anomalo and some of the interesting challenges that you have encountered of dealing with applying machine learning to this question of data quality. Definitely appreciate the time and energy that you and your team are putting into that, and I hope you enjoy the rest of your day.
Awesome. Thank you, Tobias. Thank you for having me.
Thank you for listening, and don't forget to check out our other shows, the Data Engineering Podcast, which covers the latest in modern data management, and Podcast.init, which covers the Python language, its community, and the innovative ways it is being used. You can visit the site at themachineLearningPodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at themachineLearningPodcast.com with your story. To help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.